a series of workshops on comparison of time-varying treatment using causal inference methods. I'm honored to introduce our guest speaker today. Dr. Jessica Yang. Dr. Yang is an assistant professor and biostatistician in the Department of Population Medicine at the Medical Institute. The focus of her research is the theoretical development and application of methods that, under explicit assumptions, may answer questions about causal effects of treatments using data from real-world observational studies. Her work has also focused on increasing applied researchers' access to these methods and ideas through education and software. I have worked with Dr. Yang previously on the use of G-methods and benefited greatly from her deep understanding of G-method theory, as well as tremendous hands-on experience in using these methods. I'm confident that you will feel the same way today. Please send in your questions via Zoom meeting, Q&A, or chat functions at any time during the workshop. Jessica will answer them during the designated Q&A session at the end of the workshop, about 15 or 20 minutes. Now, please join me to welcome Jessica.
Thank you for that very nice introduction, Yi. I'm just gonna bring my screen up here. Can you guys see my screen?
We cannot.
Oh, I see. Whoops, now. Now I think you can. So, Yi, should I get started?
Yes, please do.
Okay.
All is well.
Okay. Hi, everybody. I'm Jessica Young, and today we're going to be talking about estimating effects of time-varying dynamic treatment strategies and observational studies. Today we're going to focus on some different estimators than Maya talked about in workshop 2. We'll talk mostly about inverse probability weighting and a little bit about the parametric G formula, but the primary focus, just in the interest of time, is going to be parametric G formula, IP weighting. So just to recap quickly of the workshop so far, so Yi, on workshop 1, reviewed the idea of emulating a target trial with observational data. She gave motivating examples about the effect of time-varying EPO strategies. She gave a brief intro to IP weighting and the parametric G formula. Maya then in workshop 2 introduced a more formal framework for causal inference. My understanding is largely in the context of point treatments, with some introduction to time-varying strategies, with some examples of what we call static strategies, and some introduction to dynamic strategies. And as I'm going to clarify a bit today, these are special cases of static and dynamic strategies that we would classify as deterministic strategies. So I'm going to talk a little bit about the implication of that and some other possibilities that include non-deterministic strategies. And Maya went through an estimator of these effects under explicit causal assumptions, the TMLE estimator, coupled with superlearner, which has some really nice theoretical properties. So today, we're going to extend some of these ideas or add on to these ideas in a few ways. We're going to take a deeper dive into a formal framework for causal inference in the time-varying setting. Specifically, we're going to define causal effects formally using counterfactuals of general time-varying treatment strategies on an outcome mean. In this presentation, I'm going to focus on outcomes that correspond to indicators of a failure event by a specified end of follow-up, so say indicator of all-cause mortality by the end of a 5-year follow-up. So in this case, the outcome mean translates to a cumulative risk. We're going to cover general, as I'll clarify, deterministic treatment strategies, which again can be classified as either static or dynamic, and we'll review examples in this context. We'll review the assumptions needed for identifying these causal effects with observational data from a real-world longitudinal study. We'll talk about how the choice of causal question, the choice of causal effects, coupled with assumptions and then coupled with your real-world data, leads us to potentially various estimators which have different statistical trade-offs. And he mentioned that there were a lot of questions at the end of Maya's talk about how do we choose between these methods given the optimal properties or theoretically optimal properties of TMLE plus superlearner. Why would we ever use other methods? And I'll give my thoughts about that. So we're going to use throughout a motivating example, a general motivating example. So over several decades, particularly in the height of the HIV epidemic, various questions were posed about the causal effects of following different time-varying antiretroviral therapy or ART initiation strategies on long-term all-cause mortality risk in treatment-naive HIV-infected populations. So several types of strategies can be considered. And we're going to talk about a few of those. And just to note, I'm going to use the term strategies, interventions, and rules interchangeably. So these all mean the same thing. So we can start with one example. So we might consider the causal effects on 5-year all-cause mortality risk in this treatment-naive study population of, say, the interventions initiate ART at baseline, let's say the first time you encounter the patient, versus never initiate ART at any time, say, during the next 5 years. So these strategies, again, rules or interventions, are special cases of what we can call deterministic static interventions. And in general, deterministic static intervention is any intervention under which treatment assignment at any time during the post-baseline follow-up is fully determined at baseline. So if I were to implement the strategy never initiate ART, for example, then under that strategy, I know exactly what treatment status every single individual in the baseline population is going to have at all future times during the follow-up. Alternatively, we could consider a different type of rule. For example, we could consider the causal effect on, again, 5-year all-cause mortality risk in the same study population under, say, an intervention if CD4 cell count first drops below 450, where CD4 cell count, for those of you who are not familiar with HIV, is a marker of disease progression, of immune suppression. So the higher it is, the better. The better for the patient. The lower it gets, the more the disease has progressed. So if CD4 cell count first drops below 450 at time K, then I initiate at that time. Otherwise, don't initiate at that time. And I could compare that to an intervention where I start ART as soon as CD4 drops below 350. So we can think of the first intervention as starting earlier while the patient is still has not progressed as far, and the second one relative to the first is starting later when the disease has progressed further. So these are examples of deterministic dynamic interventions as opposed to static interventions, because treatment assignment at a given time under these interventions depends on time-evolving individual risk factor history up to that time. So that's why we would say these are dynamic interventions. And the reason we'd say they're deterministic dynamic interventions is that for two individuals with the same history up to a particular time K, they are guaranteed under that intervention to have the same treatment. So an individual's treatment is fully determined by their risk factor history under a deterministic dynamic intervention. But we could consider yet a third option where we consider similar interventions but slightly tweaked. So we could consider if CD4 cell count first drops below 450, let's say, then initiate treatment with some probability, otherwise initiate with maybe a lower probability. So these interventions reduce to the interventions I described on the previous slide when we replaced, I don't know if you, can people see my mouse? They can, right? You can see me moving my mouse?
Yes, absolutely.
Okay, so I have a pointer. I'm just being sure I have a pointer.
Yes,
so if we replace probability 2/3 with 1 here, and this 1/4 with 0, then this would reduce to the deterministic dynamic strategy on the previous slide. So we classify these as random dynamic interventions because, again, treatment assignment at a given time depends on the individual risk factor history, just like the deterministic case, but we call them random because given that history, it's not guaranteed what level of treatment you will receive. It's just there's some probability associated with it. So we can think of this intervention as the case where, say, we just assign treatment according to a weighted coin flip that depends on your risk factor history. You could think of turning a random number generator that's dependent on, in this case, CD4 cell count. So, so this sort of illustrates that there are many possible ways to define a causal effect of different time-varying treatment rules, even for the same treatment. And this is because there's an infinite number of ways to define these rules. So just given the examples we went through, there's an infinite number of levels of CD4 cell counts. So just those CD4 cell based strategies, there's an infinite possible number. And then when you move to, say, random dynamic regimes, there's an infinite number of treatment probabilities. And then, of course, you could bring in other risk factors like viral load and so on. So there's many ways to define a causal effect, even for the same treatment. And how do we choose these? Well, of course, we would like to choose based on the scientific question of interest. We may have many scientific questions, but there might be one burning one at that moment in time. But this is always going to involve a trade-off between the question we want to answer and the data we have available to answer it. So, and this is because we often don't have, or we almost never have, the ideal data to answer any particular question. So what do we mean by the ideal data? Well, for any of these questions that we posed, we could answer any of them in an ideal study, which would correspond to a study where we randomized individuals from that study population of interest at baseline to one of the two strategies of interest, however we chose to define those strategies. Again, what is our scientific question? Then we somehow force them to adhere to the rule required by the baseline randomization, in other words, the protocol of the trial. So this was sort of what Yi talked about with emulating a trial throughout the follow-up, where the follow-up for an individual could be the full 5 years if they survive, or the event, whichever comes first. And then statistics is trivial. We simply could compare the difference in proportions of deaths across each arm. So proportion 1 is just the number of people who die somewhere in the 5-year follow-up in arm 1 out of the total randomized to arm 1, and then similar in arm 2, the number who die out of the total randomized in arm 2, and then we could just maybe do a 2-sample t-test. So we don't need to talk about G methods, even though here we're definitely doing causal inference and we're targeting exactly what we want. The problem, of course, is that rarely do we have such an ideal study. Even if we could conduct a large enough trial, we can't ethically force people to adhere to any rule over time. And even if we sort of consider a dynamic, realistic rule, there are always going to be unforeseen events that where people may not be able to adhere to the protocol. And of course, trials are not always feasible or timely. So the best available data is often going to come from an observational cohort study where we don't even have baseline randomization, and the study was not even designed to answer any one question that we might pose. And of course, further, whether or not the data comes from a randomized or a non-randomized observational study, people may, of course, drop out of the study or be censored for other reasons, such that outcome status under any treatment strategy is not available for that subject. So an example of a real-world study is the HIV causal collaboration, which included several cohort studies from 5 European countries and the United States. cohorts were assembled prospectively based on data collected for clinical purposes and national healthcare systems with universal access to care. So this is really sort of the optimal longitudinal cohort study. And these data have been used to estimate causal effects of many types of ART initiation strategies over the last decade or so, when particularly at the height when there were no trials available. There actually are trials available now for a lot of these questions. So we have a couple of papers where we implemented IPW and the parametric G formula that our references are at the end. I think they were posted on the web under the workshop, where we used the same subset of the HIV causal collaboration to answer these questions using some of these questions using the two methods. So in these analyses, we specifically defined the study population of interest as those who were at least, just to give you something concrete to keep in your mind, who were at least 18 years old, had never previously initiated ART, so treatment naive, no history of CD4 cell count less than 500, so these are to keeping people early, hopefully early in infection, not pregnant, and having measure of CD4 cell count and viral load within the last 6 months. So we defined the first time at which an individual met all of these criteria and the month in which their CD4 first dropped into the range 200 to 499 as their baseline time. So this is the definition of the study population, and then for each individual in that study population, the time at which all these criteria were met and CD4 first fell into that range is their start of follow-up. And just to note that this baseline may correspond to different calendar times for different people because the data range from over a couple of, almost over a decade. And we have the calendar year as a covariate in the data set. Okay, and so now I'm going to introduce, I'm trying not to be super notation heavy in this talk, but there is going to be a little bit of notation. So this just formally describes what we measure in this HIV causal data set. So in this case, we have monthly measurements of the following random variables for each subject, where little k indexes a follow-up month beginning at 0, which denotes the baseline month, the month that everybody met that eligibility criteria and first fell into that CD4 range, and going up to a maximum of capital K equals 59. So we have consider a maximum of 60-month follow-up. So here, capital AK is just the indicator of whether an individual in this subset of HIV causal initiated ART by follow-up month K. So this is a time-varying indicator, and it simply represents the observed indicator of what happened in HIV causal, nothing to do with a question yet. LK is a measured vector of mortality risk factors for death. So for example, the most recent CD4 cell count measurement, a recent measurement of viral load, whether they have progressed to AIDS, and whether a lab measurement was taken in month K, and I think there were maybe a couple of others. And then YK+1 is an indicator of mortality status by month K+1. So this is, once this switches to 1, it stays 1. It's just, did you die by month K+1? And CK+1 is an indicator of censoring by month K+1. So in this analysis, we defined an individual as censored after 12 consecutive months with no lab measurement. And I don't have it on the slide, but we're going to take Y0 and C0, so the mortality status indicator and the censoring status indicator in month 0, to be 0 for everyone. So we did restrict this to those who were alive and uncensored in month 0. L0 here, which is the measurements of the mortality risk factors at baseline, also additionally includes time-fixed baseline characteristics like sex, race, baseline age, and even that calendar year in which they meet eligibility criteria. And we're also going to use notation for YK+1, which is the indicator of mortality status by the end of the follow-up of interest. So this is their outcome status by 60 months. So in this special case, we'll just denote this Y60 to keep that example in mind. We denote the history of any of these variables with an over bar. So A bar capital K here denotes this initiation status, observed initiation status history from baseline through capital K. And finally, because we have intervals that are of a particular length here, a month long, we have to assume some temporal order within each month. So we assume the order CK, YK, LK, AK, so what this assumption means is that, for example, we assume that whether or not you initiated treatment in a given month cannot affect your outcome status within that month by assuming this Y precedes A in that month. But so we allow that treatment initiation status can affect your mortality status in the next month. And so when you make these intervals very, very tiny, say a day long or even a week long in this example, the temporal order is not going to make any difference on results. In a month long, it probably won't either. I think we actually have looked at this and it did not, at least in practice, it's not made a big difference. But if you made the interval, say, a year long, it could make a very big difference how you assume this in temporal order. So it's not that any particular temporal order is right or wrong. It's just ideally you don't make these intervals very, very long. Okay, moving on. So with these questions and HIV causal in mind, we're going to now consider a general framework for defining causal effects of any of these time-varying deterministic strategies, whether they be static or dynamic. We'll consider assumptions for identifying these effects in observational studies, like the HIV causal cohort study. Then we're going to review the key function of observed data that identifies these effects under these assumptions, the G formula, which I think Maya and Yi probably alluded to, and we'll talk about it a little bit more. And finally, then we're going to consider estimators of this function, the G formula. Most of this is going to be focused on IPW. I'm actually not even sure I'm going to have time to get through all of the material I have on IPW, but the slides are there for what I don't get through. And we'll briefly talk a little bit about parametric G formula estimators. And then if there's time, I'll briefly consider extensions to random dynamic strategies and consider why we might choose them. Okay. So we're now moving on to defining what we mean by a causal effect. In other words, what is it that we want to know really? How do we formally define this? So we're going to denote little g in general as any deterministic time-varying art initiation strategy. But if you have a particular application in your mind for your subject matter area of interest, you can think of G as any time-varying treatment strategy on your treatment or exposure. We're going to define YG60 now as the indicator of whether an individual in the study population would die of any cause by the end of follow-up had possibly, contrary to fact, he adhered to the rule G. So we're sort of imagining that in our true study population, that from which HIV causal we can think of as a random sample comes from, that for every individual in that study population, there exists a counterfactual outcome under various possible treatment rules. We just simply don't observe all of them. We might get to observe one of them. So we say that this is an individual's counterfactual outcome associated with the rule G. In this example, YG equals 1 for an individual who would die under G somewhere in the 5-year follow-up, and it equals 0 for an individual who would be alive under G by this follow-up. And I should say, actually, I called this Y, but really, oh, no, actually, we have the 60 index there. So yes, this is the indicator of mortality by 60 months. And we're also, I'll just note, we're going to consider implicit in any definition of a deterministic intervention G, the additional intervention eliminates censoring. So by this, the interpretation of the counterfactual and in turn the causal effects and the things that we're targeting in our statistical inference are going to depend heavily on our definition of censoring. So in our case, censoring was individuals were censored if they went 12 months without a lab measurement. So implicit in all of our effect estimates is we're targeting an interpretation that that we also somehow forced under all interventions everyone to have a lab measure at least every 12 months. So you have to be careful in how you define censoring, because this is going to impact assumptions and also the interpretation of the effect estimates. So for any two different deterministic ART initiation rules, or again, your treatment rules that you're keeping in mind, let's call these generically, say, a G1 and a G2. We can define an individual causal effect by the fact that we're imagining that we can define these counterfactuals, say YG1 minus YG2, so each individual has some causal effect. We can also consider the average causal effect, which in our case, because Y is a binary variable, the mean of this variable is just the probability that it equals 1. So this is a counterfactual population risk under G1, and we could consider, say, minus that risk under G2. So this is the causal risk difference comparing G1 and G2 in this population. And so we can keep in mind, again, examples of G1 and G2, maybe initiate at baseline versus never initiate, or initiate when CD4 first drops below some cutoff, and choose compare different cutoffs. So of course, I believe that patients and doctors really want to know about individual causal effects, and this is often an interesting debate within the causal inference literature. What is the question that people really want to know? And this is really what people want to know. They want to know, am I going to die in the next 5 years if I do follow this rule versus this rule? Or the doctor wants to know, when they're looking at a particular patient, how should I treat this patient? What is his counterfactual outcome going to be? But of course, it's impossible to identify individual level effects without very strong assumptions in any study, even the ideal trial that we already talked about. So we're not even going to try to consider that. But the average causal effect is much less of a reach. At least we can directly identify it, as we talked about, and estimators' statistics will just be 2 sample t-tests. And in the ideal study, of course, in observational studies, we need assumptions that may or may not be reasonable, but we can try our best in those studies to get at the average causal effect. So we're going to talk about how we might do that. So under assumptions, we can show that it's possible to link our observed longitudinal data, like that obtained in the HIV causal, to a counterfactual question like the average causal treatment effect that we just talked about, comparing 2 strategies, say G1 versus G2, and these assumptions are exchangeability, positivity, and consistency. So I think in the previous workshop, there was a little bit of review of these assumptions, but I'm going to go into a little bit more detail on these. So we'll start with exchangeability. So I have this sort of in notation, but we can go through it in English as well. So exchangeability states that for each follow-up month K in our example, and for both choices of G, let's say G1 and G2, at each follow-up time, an individual's observed treatment status and censoring, so that's these guys, are independent of his or her future counterfactual outcomes, that's these guys, as under the rule G, conditional, that's this bar represents conditioning, on his or her observed past history of the measured treatment and covariance in the study, with this history being consistent with the intervention G. So given a history consistent with the intervention G, that's what this guy means. It means A bar K minus 1, the observed treatment history, is equal to some values that are allowed under G, then his current treatment and censoring status are independent of his future counterfactual outcomes. So this assumption is not testable, and it's sort of intuitive. Why? Because we don't get to see these for everyone in the study. It does hold by design in a sequentially randomized trial where we just randomly assign a K by, say, a weighted coin flip based on past values of these guys, and where no one is censored, or were we to randomly assign censoring by these guys, but of course, there's no study in which we randomly can assign censoring typically. So in general, this assumption is not guaranteed to hold. And exchangeability, just to note, has another common term, no unmeasured confounding. And because of this, we say that the L bar K here are the measured confounders through K, or the measured confounder history through K. So again, in our example, this includes, say, measured CD4 cell count history, viral load, etc. So as we said, exchangeability is an untestable assumption. What this means is it can't be assessed in the data, again, because we don't get to observe the counterfactual outcomes for everyone, but it actually can be assessed under an assumption on how the data in the study were generated. And this assumption can be driven by subject matter knowledge or simply by assumptions when knowledge is absent and different assumptions can be considered. These assumptions can be represented graphically using causal-directed acyclic graphs or DAGs. Under these assumptions, in other words, under the assumptions of the DAG, exchangeability can be evaluated, read off the graph by certain manipulations of the DAG. So here's just an example. So this is, we'll start with a causal DAG, assuming we actually conducted a sequentially randomized trial where we physically assigned A based at each time based on L. So that's represented by the fact that A only has arrows going into it from past A and past L. And also this graph, just for simplicity to avoid clutter, only represents a couple of time points and doesn't depict censoring. So here, though, we allow that there does exist an unmeasured common cause of the outcome, mortality, and say the measured confounder, CD4 cell count. Maybe U could be a genetic factor that independently affects mortality risk in your CD4 cell count. But the idea is that if we had actually conducted a sequentially randomized trial, then the design would guarantee that there's no arrow from U into A at any time because we know how treatment was assigned and it wasn't dependent on U. But what if we drew this DAG to represent the data generating assumption on HIV causal, which was not a sequentially randomized trial, and that we only observed how people initiated treatment. We did not physically intervene ourselves. So in this case, the absence of an arrow from U into A is an assumption. So this might be a reasonable assumption if U is, say, a genetic factor, and the doctor also knew nothing about those genetics. They had no measurement of those, and they only used past L's and A's to assign treatment. But if this U is something the doctor saw to determine treatment that we just happen not to have in our data set, we'd need to draw an arrow from U into A, and again, the absence of it is an assumption. So in general, exchangeability for any strategy G, that counterfactual conditional independence assumption, is guaranteed under the assumptions of a causal DAG, where only arrows from past L's and A's go into future A's. In other words, there are no arrows from unmeasured variables into A. So that was the example that we gave before, and again, it's an assumption in a study like HIV causal. I'll just note that this type of graph is a special case, or this scenario is a special case of where exchangeability could hold, the case where there are no arrows from U into A at any time. In other words, you could draw a graph where there are arrows from U into A's at some times, but other arrows are potentially removed, in which exchangeability would be consistent with the graph. And this follows from a more general sort of algorithm for reading exchangeability off of a causal DAG by the absence of unblocked backdoor paths, this is due to work by Judea Pearl. So in the interest of time, I'm not really sure how long this presentation is going to take. I haven't timed it, so I've moved a bunch of slides at the very end that talked about this general criteria for reading exchangeability off a graph, with an example taken from Jamie Robbins and Miguel Hernan's longitudinal effects chapter. And if we have time, I'll go through it. If not, you can go through that and look at some of the references. Okay, so we've now covered exchangeability a bit, what it is and how we might evaluate it under assumptions. Now we'll talk about the second assumption, the positivity assumption. So in general, positivity is specific to the choice of strategy. So in general, we can define positivity as the assumption if a particular level of the assumed measured confounder history through K is possible to observe in the study population, then it must also be possible to observe individuals with current treatment status consistent with that strategy. So for those of you who know a little bit about positivity, This might actually sound strange, and that's because usually positivity is not stated in general. It's stated only for the case of static strategies. So this is giving you a general definition of positivity, and we'll talk about it to clarify that in the context of a couple of examples. So we'll consider the first example of a positivity violation. So suppose we consider a deterministic static strategy, again, never initiate art. So this might be one of our choices of G1 or G2 in defining our causal effect, and assume, perhaps or hopefully motivated by causal diagrams, that we assume CD4 cell count history is part of L bar K. It's needed to ensure exchangeability. And also assume that in the real world, in the study population from which HIV causal is a random sample, some individuals it's possible to see individuals who have CD4 measurements fall below 350 during the follow-up. So in this case, and also suppose by clinical guidelines at the time in which this population exists, any individual who has a measurement of CD4 fall that low is going to have initiated treatment already. So in other words, people are not ethically, doctors are not ethically waiting that long to treat people. So basically it's possible to observe people with CD4 cell count history that low. Everyone who has CD4 that low will be treated, and our question is never initiate ART. So this is an example where we have a positivity violation because it's possible to observe levels of CD4 cell count history, a component of our assumed L bar K vector, such that no one with that history has data consistent with the specified treatment strategy. So in this case, we have a positivity violation. But suppose we kept everything else the same, but now simply changed our definition of the strategy. Instead of considering never initiate ART, we considered the deterministic dynamic strategy, initiate ART in month K if CD4 first drops below 350, otherwise don't initiate. In this case, the fact that in the observed data or in the observed world, individuals who drop below 350 always start does not result in a positivity violation because the strategy says you should start when you drop that low. So, so basically, a solution to positivity violations can be to change the question to one that is better supported by the real world data. And dynamic strategies are, because people are always treated dynamically, treatment decisions are going to change based on measured risk factors, right? As the doctor is going to make treatment changes based on how the patient is doing, real world strategies are dynamic. So considering dynamic strategies can be a way to avoid positivity violations. And as I said before, positivity is often mistakenly understood as the assumption that there are treated and untreated individuals at each time within all levels of the confounder history. But as we just saw in the example, that's only the case for certain types of questions. You can always change the question to avoid a positivity violation by making it closer to what you see in the data that's creating the problem. And unlike exchangeability, positivity at least is in principle a testable assumption in the sense that it corresponds to something about the distribution of observed treatment in the data given the observed measured confounder history. So there's nothing required about knowledge of counterfactuals with respect to positivity. And finally, we have the consistency assumption, which is often kind of swept under the rug. But what the consistency assumption states is that if any individual's observed treatment history is consistent with the intervention G, then his observed outcome equals his counterfactual outcome Y. That should have been Y60G. So what consistency allows is the assumption that we can link the observed data to the counterfactual outcome. And for many people, they think it's sort of natural to think of this as a definition rather than an assumption, but in fact it is an assumption. And whether or not it holds depends on how precisely we define the counterfactual outcomes, or how to assess whether it holds. It's very much dependent on how precisely we define the counterfactual outcomes. So to understand why this is an assumption, let's consider a case where it could be violated. So that's always the best way to understand assumptions, is consider how they're violated. So let's consider a simple case where we define the strategy of interest G as initiate treatment at baseline. So here, YG60 is the counterfactual mortality status, had an individual initiated ART at baseline. Okay, but what if the value of this outcome depends on the dose of treatment? And in the real world, people receive different doses of treatment. So for any individual in our study who initiated treatment, our question is it guaranteed that his observed outcome is going to be equal to YG? This would, if that were true, then this would be a definition and not an assumption. But it's assumption because the answer is no, if by initiate treatment, when we define G, we really mean initiate some specific dose of treatment, say 20 milligrams. By contrast, the answer would be yes, if by initiate treatment, we mean more precisely initiate according to how treatment was initiated in this particular study. So if we consider the meaning of G to be this one, then it's not guaranteed that simply because you initiated that your counterfactual equals your observed. But if we make our meaning of initiate link to dose in a more flexible way that links to the study, then yes, if you initiated, then your counterfactual outcome equals your observed outcome. Now, in some cases, so you might say to yourself, this seems a little bit sort of intellectually not important, but it is for one reason, which is that which I actually don't have on this slide, but if you were to interpret the results of your study, even if all of your assumptions hold, and then you move to a new population and dosing has changed, then you could get a very different answer by not being clear about what or surprising answer by not being clear about what you meant about dose with respect to initiation. But another problem is that in some cases, it's actually almost impossible to define precisely what we mean by the intervention G. And in this case, we'd say the counterfactuals are ill-defined. So for example, if we were to consider an intervention that sets BMI to 20, there are many factors that could affect the counterfactual outcome in that way, because there's many ways that you could set BMI to a particular value. So this is a case where it's very hard to evaluate the consistency assumption. Another common example is when you have outcomes, unlike our all-cause mortality outcome, sometimes we consider outcomes that are subject to competing events. So for example, in the HIV world, death by, say, tuberculosis might be of interest, but some individuals are going to die of cancer during the follow-up. So one approach that people have taken is to consider death from competing events a censoring event, which, as we talked about before, all of our interventions incorporate the interpretation, eliminate censoring. So those interventions are very ill-defined. And actually, it's been sort of made clear in some nice papers by Miguel Hernan that when you have violations of consistency due to ill-defined interventions, the violation of other assumptions like exchangeability and positivity become more likely. So I don't have these papers here on the slide, but there's a nice one called Does Water Kill? And another one, the first author is Sarah Taubman with Miguel, that's on BMI interventions, and in case you're interested in looking at those. Okay, so now we've outlined our three core assumptions for any that apply to any strategy: deterministic or static or dynamic strategy, exchangeability, consistency, and positivity. And so Robbins in the sort of mid-80s gave the seminal result that showed that given these three assumptions for any strategy G, we can identify the population mean of the outcome had contrary to fact, everybody followed that strategy G by what he called the G computation algorithm formula characterized by that strategy. And in recent years, that term has been shortened to the G formula. So the G formula we can understand as really a population parameter. So just like you learned about in your intro statistics classes, about, say, a population mean difference might be a parameter that you might consider different ways of estimating, or a population variance, or any type of population parameter, the G formula characterized by some G and contrasts in this function under different choices of G, say G1 versus G2, which now, by our previous arguments, identifies a causal effect as a function of the observed variables as opposed to counterfactual variables. So this is our population parameter, and it can be estimated just like any population parameter using some statistical procedure in a sample from the target population. So in our example, this sample are those individuals who meet criteria for being part of the population at baseline in HIV causal that we outlined. The problem, so we talked about the original challenges of untestable assumptions in causal inference. You know, we have to make some stretches, we have to make a lot of assumptions to start, even to claim that the G formula is a reasonable target parameter. In other words, it equals what we really want, which is the causal effect of G1 versus G2. The problem, the next challenge we have to face is that the G formula characterized by any particular G is typically a very high dimensional function. And that dimension is driven by a few things, including the number of follow-up times k. So in our case, this is 60, which is a lot of times. And also the dimension of the measured confounder history, L bar k. So in our case, for example, this includes CD4 cell count, viral load. These are, unless we sort of make further assumptions, these are continuous variables. And so here we're not, you know, we don't have to worry too much about understanding this immediately, but I'm just showing you what the G formula looks like for any particular G, and we're going to describe it in words on the next slide, but you can see it's kind of a nasty function, and what we're trying to do is estimate maybe the difference of this formula for different choices of G, which are indexed here, and we'll explain what that means now. So what is the G formula? This population level quantity that we're going to try to estimate with some statistics. So we can think of it as a sum or an integral in the case where the L's contain continuous covariates over all possible levels of the measured confounder history, which again, we have our running examples. That function, so this is, here we'll just go back and show, so this is that sum. And then that function is summed over a function of time-varying conditional hazards. So, so that's these guys, and these are really, I'm calling these hazards, they're really discrete conditional probabilities of failing in a given month, given you survived to the previous month. Each term in that function is conditioned on one particular level of the confounder history in the sum, and two, the treatment history allowed under G for that confounder history. So because we're only for now considering deterministic interventions, for any level of the confounder history, there's only one possible treatment history allowed. That's what makes it deterministic, which is why we only have a sum over L bar k, because there's only one possible level of these given a level of these. And so then this sum over all confounder histories is weighted by a function of the joint distribution of those time-varying confounders, specifically a product over all times k of the chance of seeing that level of the confounders at that time in the population, conditional on that level of the confounder history, and treatment history consistent with G through the previous time. So that's a bit of a mouthful, but that's basically these guys, which are product for each time k here, product again from 0 to k. So it's a complicated function. So in other words, it's a messy function. So even if we could reasonably argue the first challenge we've overcome of our causal assumptions holding, additional constraints are going to be needed in practice to reduce the dimension of this estimation problem, either through the use of parametric models or maybe machine learning, like Maya talked about the superlearner. Different estimators are going to impose constraints on different features of the data. So these estimators include inverse probability weighting, parametric G formula, TMLE, and in fact, there are more estimators. For example, there's a sort of variation on TMLE that involves estimating sequential sequentially nested means. There's actually another methodology called G-estimation, which is completely different than G-formula. It's not a G-formula, it's an estimator, which makes other assumptions. And all of these are there because this is a hard problem and you have to make decisions, and there are going to be trade-offs in those decisions. So the choice of estimator, and even within each of these estimators, which makes this even more complicated, is there are many, many potential implementations. So for example, TMLE is not one method. There are, even at this point, probably 10 different implementations of TMLE that all are going to involve trade-offs. And the trade-off is going to require you to decide, do I rely more on data or more on model constraints? And sometimes that's going to be, and that's linked to what we originally talked about, which is the choice of questions. So when you have data that well supports your question, you can rely more on data. When you don't, and you insist on answering that question, you're inevitably going to rely more on model constraints. So now we're going to spend probably the bulk of the rest of the time, although I think I'm making good time, so I might, I'm talking fast, I guess. I might have time to get through everything here. So, so now we're going to talk through and motivate inverse probability weighting, as well as various implementations of inverse probability weighting. And I'll just note that a lot of these choices within inverse probability weighting also apply to TMLE. So IPW estimators are what we call semi-parametric estimators, in that they don't require parametric specification of the whole observed data likelihood. So the whole observed data likelihood, if you think back to that slide where I gave notation for HIV causal, where we can think of the whole data is A bar K, L bar K, all the way from K equals 0 to K, all the history of the Y's. So you can imagine having there's a joint likelihood that exists on that observed data function, and these are semi-parametric estimators because they don't require me to represent that whole likelihood by a set of finite parameters. Any implementation of IPW is going to require consistent estimation, meaning that as the sample size gets bigger, it converges to the true value of what we call the observed treatment mechanism. So in the case of survival outcomes, which is what we're talking about today, by observed treatment mechanism, I mean either the density for a continuous treatment, or in our case, the probability function for treatment at each time in the observed population. So in the population from which HIV causal is drawn, conditional on past measured treatment and confounders, and surviving and remaining uncensored to each time. So in our example, the chance of any level of treatment initiation status by each K, each level of treatment initiation status, there's only 2 levels, 1 or 0. So what we're talking about is the observed chance of having either a 1 or a 0 at each time K, conditional on your measured past L's, past A's, and surviving and remaining uncensored, 2K. So we denote it with this FOBS here to denote that it refers to the treatment mechanism, or at least the distribution of treatment given the measured past in the observed world, not in any counterfactual world. And just to link this to maybe terminology that you've heard before, when we plug in an AK equals 1 here, then we call this FOBS the propensity score at K. So for those of you who have heard the term propensity score, the propensity score is the observed treatment mechanism for a binary treatment evaluated at 1 treated. And as we'll see, IPW estimators also require generally consistent estimation of the censoring mechanism when we have censored data, which we typically always do, where the censoring mechanism is the probability of being censored at a given time. In our case, this was CK equals 1, also given the measured past. So these are the 2 things you have to get right. You don't have to specify everything, but you have to consistently estimate typically those 2 things. So now we're going to give a little motivation for why IPW estimators work. In other words, why they may be consistent, converge as the sample size gets larger to the true population parameter, which now is the G formula. Why is it the G formula? Because we made those 3 exchangeability, consistency, and positivity assumptions, and in that case, the G formula equals the causal parameter we want. And this is because the G formula characterized by an intervention G has an algebraically equivalent IPW representation. So remember the G formula was that high dimensional sum over the L bar K. It turns out that you can just rewrite it, this is just algebra, as a function of weighted discrete hazards. So that's this guy here, where the weighted hazards at each time are, again, hazards meaning discrete hazards, are just defined like this, where expectation here means just a mean. The weights, WKG, are specific to the choice of G and the time K. And also the weights will depend on individual characteristics like the treatment confounder and censoring history of that individual. So let's go into what are these weights. So for each person in the population who has not yet failed by time K, the weight WKG is defined at time K, and for a particular strategy G, where we pick the strategy G, right, that's part of our question, as a particular ratio. So the numerator of the weight WKG basically just takes the value 0 if the individual has a treatment history inconsistent with G from baseline through any follow-up time K, or if that individual is censored in that period. Otherwise, it takes the value 1. So this is sort of a technical description. I'm going to get to sort of a summary of this on the next slide if this is looking overwhelming. So for example, if we chose G to be initiate ART at time K, if CD4 first drops below 450, otherwise don't initiate, then any individual in our target population who at time K has never had a CD4 value drop below 450, but has started treatment at K, is going to get a 0 in the numerator of WKG because they're not following G by that time. And the denominator of WKG is a product over all times from baseline to time K. So remember, WKG is different for each K. It's going to be the product from baseline all the way to the current time K of that observed treatment density that we just talked about times the probability of remaining uncensored given the measured path. So really we can think about this side together as the probability of adhering to the intervention through time K given that individual's measured path. So a simple translation of all of that can be boiled down simply to the following. For a person doing the wrong thing with respect to G, anywhere between baseline and time K, their WKG is 0. For a person doing the right thing at all times between baseline and time K, their weight is 1 over the chance of them doing the right thing in the observed data given their past. So that's what it means. Okay, so one thing to sort of remember is that when I'm defining this WKG, this is still, we're still at the population level. We're not yet talking about estimators. This is just the weight that defines the IPW representation of the G formula, which again is something we're trying to estimate with some statistical method. So this result, just this existence of this algebraically equivalent IPW representation of the G formula, gives us a fairly simple approach to estimating contrast. And G formula is characterized by a G1 versus a G2. Again, why are we doing that? Because under our causal assumptions, this contrast equals the average causal effect. So a fairly simple approach is just sort of characterized by 5 basic computational steps. The first is creating a person-time data set, which is just a reformatting of the observed data. The second is making copies of the data for each strategy G we consider. The third is artificially censoring each copy as soon as the data is inconsistent with the G indexing that copy. And the fourth is computing inverse probability of censoring weights based on that artificial censoring. And finally, the fifth is computing weighted hazards and cumulative risks, and that computation is going to match the, I'll just show it again, this inverse probability weighted representation of the G formula. So we're going to delve into some of this in the next slide. So I'm going to basically start with reviewing this basic implementation, but then if we have time, I'll talk about there are many, many extensions and modifications in special cases of this approach and various reasons for considering them. Okay, just a sip of water here. So we're going to use as just a running example. Suppose our interest is in estimating the effect of these CD4-based initiation strategies that we've talked about, say start when CD4 first drops below 450 versus 350. But again, you can think about in your mind any two strategies that you might want to compare in your research. So going back to this basic IPW algorithm, step one. So the first step is we're going to construct a person-time data set. So the way this data set is going to look is that it's going to have columns. One column is going to be index ID, which is a unique individual identifier. K is the month of follow-up, starting always at 0, the baseline month, and going up to a max in our example of 59, so that there's a max of 60 months. AK is our treatment indicator in month K. LK are our time-varying covariates, where we have one column per component of that vector. So again, the CD4 cell count, viral load, etc. CK+1 is a censoring indicator, YK+1 an indicator of failure. So in this person-time data set, we're going to construct it such that the first line on which CK+1 equals 1 for an individual ID, in other words, the first month in which they're censored, is going to be the last record in the data set for that ID. On that line, YK+1 is coded as missing. Also, the first line on which YK+1 is 1, so the first month in which a subject dies, is going to be the last record in the data for that ID. Any individual who is never censored and never fails throughout the follow-up is going to have capital K+1 records, again, 60 records, with the whole column of Y and C for that ID being equal to 0. And in addition to these columns, generally we're going to create additional columns with functions of history of the treatment and confounders, and the reason for that is going to be for estimating the weight denominators, and we'll talk a little bit about that. And the ID obviously is going to take values from 1 to n, where n is the number of individuals in our HIV causal example who met that baseline eligibility criteria. So every individual ID is going to have at least one record, but they might have fewer than 60 records depending on if they were ever censored or failed. And also in this data set, we're going to include time-fixed baseline confounders as, again, their own columns, but the values will be repeated on each line for that ID. So remember, this step is just configuring the observed data. It so far has nothing to do with our question, how we define G1 or G2. And this just illustrates for one ID how I just made this up, but what this might look like. So this is ID 1, so he has 7 months of follow-up. He fails at month 7, so this is the last record in the data for him, right? So this is just what ID 1's records look like in the observed data. The second step is we're simply going to take the observed data set that we just constructed and make 2 copies of it. One is going to be indexed by the first strategy of interest, and the other is going to be indexed by the second strategy of interest. So that's step 2. Step 2 is very quick. Step 3 is artificial censoring. So now in each of those G-specific copies, we're going to create an indicator of artificial censoring. An individual will be artificially censored in the first interval his data becomes inconsistent with G. So in this copy, at the time he is artificially censored, this is going to be his last record in the copy, even if he had more records in the original data. So for example, an individual might have failed in the real data at time 7 or been censored at time 4, but he might be artificially censored in the copy G1 at time 2 because his data became inconsistent with G1. So this is what we're saying here. So the same ID may have different numbers of records, or fewer records really, in the original copy, in the copy G or copy G2 than in the original copy. Okay, and so for example, for the G2 copies, they initiate as soon as CD4 drops below 350. Otherwise, to initiate, an individual who initiates at some time when CD4 has not yet fallen below 350 will be censored at the time. And similarly, an individual who does not initiate when CD4 first falls below 350 will be censored at that time. So basically, as soon as they they stray from what's allowed under the intervention. So this just illustrates that. So the top part here is the original records for ID1 that we showed before, and this just shows what his data looks like in the artificially censored copy for G equals start art when CD4 first falls below 350, because his A switches to 1 when his CD4 hits 430 for the first time, and so we censor him there. Even though he has 7 records in the original data set, he only has 4 records in that artificially censored copy. This just shows what his records would look like in the copy start cart when CD4 first falls below 450. Here, his original data looks the same as his copy G1 data because he's actually following that intervention. He starts art when his data first drops below 450. This is the first time it drops. It drops from 456 to 430, and he started. So we keep all of his records. He's doing the right thing. Okay. Now we get to step 4, which is construction of inverse probability of censoring waste, which is the most involved step. So let's get to this. Okay. So so now we get to the weight construction. So now in each copy, we're going to estimate the probability of not being artificially censored at each time. In other words, doing the right thing at time K under G, conditional on past treatment and confounder history, and also previous survival and previously being free from all censoring, artificial and real censoring. In our example, that was due to not coming in for a lab measurement. So we actually don't have to actively worry about conditioning on 2 by the way we constructed our input data set, because we've tossed people as soon as they fail and as soon as they're censored, right? So that's actually allowing us, that's sort of implicitly conditioning all later computations on that. So that's kind of why we do that. But for one, the past treatment and confounder history means the confounder history through K and treatment through K minus 1, because given this path, artificial censoring status is fully determined by your current treatment status at K. So in other words, when we estimate the probability of not being artificially censored at time K, what we're really estimating is the probability that treatment takes the right value according to G, given past measured confounders and previous adherence to G. And this is precisely that F obs that was in that original weight denominator. Okay. So this is where these sort of issues arise, right? Because the measured confounder history L bar K is high dimensional. So in order to estimate that probability of being artificially uncensored or censored, and then 1 minus that is the probability of being uncensored, given L bar K, you're going to have to make assumptions to estimate that probability, because there's no way you could, say, estimate it by a contingency table, non-parametrically. So one very simple approach is to just fit a pooled logistic regression model pooled over time. So using the pooled over time data in the artificially censored copy, we make the dependent variable, we fit a logistic regression where the dependent variable is an indicator of artificial censoring. So just going back to what that looked like, so that was like this guy in copy G1 and this guy in copy G2. So that's our dependent variable. And the independent variables will be a function of K because it's pooled over time, current values of the confounders on each line K, and past values through K minus 1. So this is where we need to create more columns for functions of history. So say we might create a variable to reduce the dimension of the whole history to a cumulative average of CD4 cell count through each time, or maybe several lagged values in the previous months on each. So on each line K, you might create a lag 1, lag 2, lag 3, depending on how much data you have and how flexible you can be. So in our case, just to sort of talk a little bit about the specifics of this example, in our example, if you initiated treatment by the previous time and were not already artificially censored, in other words, you're still in the data, then you can't be artificially censored at a future time, because the only way you get artificially censored is by starting wrong. So once you've started, either you've been artificially censored, or once you've initiated, either you've already been artificially censored or you've done the right thing, and so you're not going to be artificially censored again. So this logistic regression model can be restricted to person time records with AK minus 1 equal to 0. So sort of to explain that another way, I know that the probability of being uncensored at the current time and all future times is 1 if you've already initiated treatment in this particular example. So I don't need to sort of blindly fit a logistic regression model over all records in this case. I can use my a priori knowledge here of the probability for records where the lagged value of A is 1, and just I'm going to use that knowledge in the construction of the weights, but for the model, I'm going to fit it to records where I have no knowledge of whether or not at the next time an individual would be artificially censored. So that's going to be why I'm fitting the model. So this just gives some sample R code. Actually, I'm not that consistent about providing code, but I do it in this case. So this just shows, like in R, how you could fit a model for the for artificial censoring and copy, say, 450. Here, for example, I might assume it's a cubic function of time, the current value of CD4, the lagged value 1 month back, your current age status, whether you've progressed to 80 time K, and maybe I make a sort of strong assumption that the whole viral load history is captured by the cumulative average of that history. And then I can include some baseline covariates like baseline age. And we'll also assume that this data set, which I've called copy 450 restrict, this is the 450 artificially censored copy, is restricted to those records where the lagged value of A is 0, because again, that's where I need to estimate this probability, and I don't have a priori knowledge. And of course, you could alternatively use like superlearner here. So based on what Maya was talking about, to estimate these probabilities could include different candidate functional forms of a parametric model or different types of machine learning algorithms. Of course, in this case, we don't have the optimal properties that TMLE has with machine learning, but you could use it, and people have found in practice that it can be useful to use this. Okay. So next, we're gonna use the model or whatever algorithm we use to estimate the probability of being uncensored given this high dimensional path, to get an estimate of the probability of not being artificially censored in each data copy at each time K for each ID for individuals who are uncensored on line K. Because again, for individuals who are censored, their weight is going to be 0. So now you're going to use this information only to give a non-zero weight to individuals who have to lines that don't have censoring. So let me make that a little clearer. So the idea is you're going to be adding a weight variable to this data set. All of these records, oh wait, no, that's not a good example. All of these records are going to get non-zero weights. This record is going to get a 0 weight because he was censored. So now we're figuring out how do we construct the non-zero weights for these records. So, okay, so in our example, for those with a previous value of the initiation indicator equal to 1, these are the examples where the probability of being uncensored is 1. Then I'm just going to set the probability 1. This is the case where I have deterministic knowledge and I don't need to use the model. This isn't going to be the case in all of your applications, but you can always think about, is there something I know about the probability of censoring that maybe I can avoid a model, or sort of an algorithm that has uncertainty in it, and use something I know about the process. For those where I don't know whether or not with certainty they're going to be censored, then I'm going to use the model so I can predict this probability from my model fit, let's say, using that individual's observed covariate history. So for example, you could just use the predict function in R. And I'm going to call each of these estimated probabilities, no matter how I got them, whether they're from the model or whether they're a priori knowledge, as p hat I k g. So the hat means it's an estimate, the I means it's to a specific individual, and k is for a particular month, and g means it's for the g specific copy. So once I get all of these probabilities at all times for all individuals and for both copies G, for each record that, again, is not artificially censored, because those are the only ones without a zero weight, on line K, the artificial censoring weight is going to be the product of those probabilities from time 0 all the way up to the current line. So on the first line, it's just going to be 1 over that at time 0, but then on K equals 1 lines, it'll be 1 over this guy times 1 over p hat I1, and so on. And then, of course, again, for each record that has a censoring indicator equal to 1, the weight is just set to 0. Okay, so this was all about artificial censoring. Of course, there's an analogous procedure for actual censoring. So when there's actual censoring the data, again, in our example, individuals were censored when they had 12 months without a lab visit. We need to additionally construct weights for this actual censoring, and it's really an analogous process. We're going to estimate the probability of being actually censored at each time, again, in the each G-specific copy. We can use a pooled over time logistic regression model conditional on the past, a flexible function, hopefully of past history. And then, again, it's really the same process. We're going to estimate the probability of not being actually censored in each data copy. We could say if we fit a pooled over logistic regression model to all the records, we could just use, again, predict in R. Or if we had deterministic knowledge, we could incorporate that instead of basing it on the model. And again, the actual censoring weight is going to be the product of those estimated 1 over the estimated probability of not being censored. I've just indexed it by C instead of G here because it refers to actual censoring. And similarly, the actual censoring weight for records actually the actual censoring weight for people who are that should be actually censored is set to 0. Okay, and then the final weight. So this was, as I said, this was a long procedure. The final weight for each ID n time k copy is going to be the product of the artificial censoring and the actual censoring weights. So this is a mouthful. If it was too much to process, you can go through it in your own time. So now let's do a step 1 to 4 recap. So we construct the person time data, we create copies, we artificially censor, and we construct the person time weights. The last step is we're just going to do an analogous computation to that, that IP weighted representation of the G formula. We're going to plug in estimates of the weighted hazards, where the weights are those estimated weights, and the denominator is going to just be of each of these guys is going to be the sum of the weights of all time k records left in the data set. Because again, we toss records after they fail or are censored. So of all the records that are sitting in the data set, it's just going to be the sum of the weights in each copy. So the copy is, we're going to do this separately for each copy. So we'll do this for G1 and then again in the G2 data. And the numerator of each of these guys is going to be the sum of the subset of those records who failed, who had a Y equal to 1. So we can repeat this process in each copy, take the difference if we want a risk difference, or ratio if we want an estimate of the risk ratio, the causal risk ratio, and then we can use a bootstrap procedure, let's say for the 95% confidence intervals. We can use, it's not terribly hard to get analytic confidence intervals for each of these lambdas. It gets a little messy to try to get it for this whole function, so I tend to use the bootstrap. And that's the basic IPW. So that's a very long description, but so there are variations on this. For example, in this basic implementation, which basically just set the weights in the procedure to be estimates of those WKGs, which just 1 over the probability of adhering to the intervention given your data, and 0 otherwise, these weights can be highly variable because the numerator is always going to be 1. So this can perform very poorly, for example, when there are so-called near positivity violations, which means the chance of, so remember, true positivity violations means given your measured confounder history, the chance of adhering to the intervention at the next time is truly 0. But sometimes we might have near positivity violations where it's not 0, but it's very rare to see someone adhering given that past. And so then what's going to happen is the denominator is going to be very, very small, and the numerator is 1. And the weights can really blow up, and the performance of the estimator, in this case, the IPW estimator, can be quite bad. So stabilized weights can help in this case. So what stabilized weights effectively do are multiply the unstabilized weights, the original weights, by a constant function. So one convenient constant that doesn't substantially change the basic algorithm we went through at all is to just take the product from, again, on each line k in constructing the weight, take the product from baseline to the current value of the probabilities of being uncensored at each time, just given survival and remaining uncensored, without reference to, without conditioning on the treatment and confounder history. So these numerator probabilities in this case can just be estimated by proportions in the data. So this has the advantage of not really changing the basic algorithm at all, but or much at all, but sometimes this doesn't help that much, because the idea of adding these stabilizing constants is to sort of bring the numerator closer to the denominator. And when you don't condition on anything, like any covariates, it may not help that much. So one way to check if it helps is to look at the weight distribution. For example, do you see extreme weights? Is the distribution of the weights highly skewed? And also, as hopefully we'll have time to talk about later, maybe during the discussion part, is how off is your estimate from that obtained using other methods? Because when you get very different estimates, so this is sort of almost answering that question of that came up, I guess, at the end of Maya's workshop. Why would you consider other methods? Sometimes using more than one method can, when you get drastically different answers, it can be a sign that you have near positivity violations. And in other words, the data is not, the question is not well supported by the data. So that can be a reason to use more than one method. So now we can take it a step further. So we've now already talked about 2 variations on IPW. We can consider even more to get better stabilization of the weights. But this solution now is going to require more model assumptions. So for example, a modification of the algorithm that we just described, that 5-step algorithm, changes step 5 so that instead of a weighted, what really corresponds to like a weighted Kaplan-Meier computation or product limit estimator, we impose a marginal structural model on each of those lambda kg functions, those weighted hazard functions, conditional on some subset of the baseline covariates, L0, and estimate the coefficients of that model and then transform them back to get estimated hazards and then back to risk. So, for example, if we selected the subset, which we can call V, as race and sex, we might assume that, say, the logit of that lambda function equals beta 0 plus a linear function of k. This is an indicator of whether G is G1 or G2, race and sex, let's say. So this is a restrictive model. So now on top of the restrictions we've had to make in estimating the weight denominators of the treatment and the artificial censoring and real censoring mechanisms, we now have to make another assumption. But if we're willing to do this, we can actually get better stabilization of the weights. Because in this case, we're allowed to make the numerator of the weights a function of V. So the larger we make V, for example, if we made it contain all of L0, then we might get the numerator even closer to the denominator. So how does this change in the algorithm work? Well, now everything's the same. We make that original person-time data structure. We make the 2 copies. But now we can stack them, the two artificially censored copies, and create a new column that's indexed G, let's say, or an indicator that G equals G1, which takes the value 1 if the record comes from the G1 copy and takes the value 0 if it comes from the G2 copy. So this is like a new variable in the data set. It's not going to vary by ID or time. It's just going to vary by which copy it refers to. And then we can fit a weighted pooled over time logistic outcome model with dependent variable Y, the Y column, and independent variables, a function of which copy the data came from, time, and also V. And so again, we could choose V to be a subset of L0 or all of L0. And so the bigger we choose V, the more variables in V, the more we're going to be able to stabilize the weight, but the stronger our model assumption is going to be, because we have to make just more assumptions about the relationship between more variables. And then the weights are defined as in the basic algorithm, but with each term in the cumulative product. Now, instead of multiplied by the marginal probability of being censored, say in the sort of simple stabilization case, we now can estimate this probability conditional on V. So actually, then you sort of have another model, although that model actually doesn't need to be correctly specified because it can be any function of V. It doesn't have to be the true probability, but if it is, it might make the stabilization better. This is just sort of justifying sort of theoretically why we can do this. Some people care about this, some people don't. But the point is here that this procedure is now targeting these weighted estimation of these weighted hazard functions, but now conditional or within levels of the selected subject V. So any function of this subset of V, which includes that numerator of the weight that we just described, the probability of being censored given V, are constants within levels of V. So this is why we're allowed to do that, and all the properties that we want of the estimator still remain, or hopefully remain, consistency and so on. And these weights tend to get less variable, as I said, as you include more components of L0 in V, but again, this is at the expense of a stronger marginal structural model because you have to condition on the whole V and specify correctly that this hazard now conditional on the whole V. So a special case where we choose V to be empty, we're back in the previous simple stabilization approach and we don't need to make an MSM assumption, but again, the weights are likely not going to be helped all that much. And this is just, in the interest of time, I'm not going to go through this much, but this is, you can look at this on your own, but this is just adapting the algorithm now to these other stabilized weights. Okay, so we talked a little bit about the need for a marginal structural model when we want to stabilize the weights better using functions of V in the numerator. But there are other reasons we might consider marginal structural modeling beyond this. And this is because when we only consider two choices of G, a lot of people, as you can imagine, might be artificially censored. There may be many, many people out of the original N subjects who aren't following either of those strategies. There's no guarantee, like, again, because this study was not designed to answer any one question. So it's really going to very much depend on how you specify these strategies, but it's very possible, particularly for deterministic strategies, which are so strict in what they require, you might find very few people are following one of two strategies. So even if N is very large, very few people may actually contribute at the end to the weighted estimator. You're going to have a lot of zero weights, in other words. So we can get around this, by get around meaning we can get around it with more assumptions by imposing an even stronger MSM assumption to use more data, but again at the expense of more potential for bias. So for example, in the case of CD4 count, there's a very natural model that arises. We could consider a whole host of strategies, CD4-based initiation strategies, not just 350 versus 450, but say lots of levels of X, cutoff X, say 450 to 200 in increments of 50, or even more if we made smaller increments. So you can imagine that the more strategies considered, the more the chance that you're going to find every individual following at least one of those for some period of time. So we can denote each of these strategies G of X, and the idea here is kind of a straightforward leap. We're, instead of just making 2 copies now, we're going to make a copy for every level of X that we consider. We artificially censor, we create weights, and now we can fit a weighted outcome regression in this case. Before, the function of G was just an indicator of G1 versus G2. Now it could be just a function of X, and if you really wanted to be, make a strong assumption, you could make it a smooth function of X, like linear or cubic, or use machine learning. So the more levels of X we consider, the more data we're going to use, the more follow-up we're going to use. But the stronger assumption, again, this model is going to be making. On the flip side, if the assumption is right, our ability, we're going to increase the precision of our estimate of the G formula contrast comparing, say, 350 versus 450. But if it's wrong, we're going to increase bias in our estimate. And of course, this particular model can answer also a lot more questions, quote, answer, meaning if the model is correct, you could, for example, in principle, report curves as a function, risk curves as a function of X. And this is just briefly, I think I have like 10 more minutes before we go into, yeah, I've got a lot more to cover. So, well, I'm going to skip into the parametric G formula in a couple of minutes. But I just want to make this point because I think people often get lost about this. So in the literature, there's been a really big separation between estimating effects of static deterministic strategies using marginal structural models and dynamic strategies. It's almost sort of considering them as completely separate methods. And in fact, everything that we just talked about also applies to static strategies. You could use precisely that copying and artificial censoring approach for any deterministic strategy G, including static strategies. So let's think about the reason that we don't use that method explicitly is because a very natural MSM arises when we limit our attention to static strategies. So for example, for our initiation example, all such static strategies are covered by do not initiate art and initiate art at time k for every level of k equals 0 to capital K. So every individual, this is an example, we just talked about the need for a marginal structural model for using more of the data. This is an example where every individual in the data is going to have data consistent with one of these interventions. So if we impose a model over all of these static interventions, we're actually guaranteed that everybody is going to be able to contribute. They're going to be following the strategy corresponding to their observed treatment pattern. So this is why the algorithm seems different for this case, because it turns out that in this case, the function of G is, when you fit the marginal structural model, is just a function of the observed treatment pattern, A bar. So in order to estimate effects of static treatment strategies, you just, fitting an MSM for the hazard boils down to fitting a pooled over time logistic model with, again, dependent variable Y, but instead of having a G or GX function here, you just have A bar that is a function of G because it's a static strategy. And again, K itself, and again, possibly V if you use stabilized weights. So again, this is potentially a strong model assumption because this is really definitely smoothing over lots of possible strategies. And also, as we discussed before, these questions are typically not well supported by data, where we almost always have positivity or near positivity violations. But it makes for a very simple algorithm and an ability to use a lot of the data because, again, everybody is following any particular static strategy. Okay, and I'll just briefly talk about grace periods. So another way to improve precision, and this sort of moves into the random dynamic strategy solution. Remember, deterministic strategies, whether they're static or dynamic, are very tight rules. They're very strict in what they require. But another way is to consider a grace period. So for example, we could consider a modification of those strategies, CD4-based strategies that, say, initiate treatment within M months of K when CD4 first drops below some level, otherwise don't initiate. And for example, we might choose M to be 6 months. So in this case, we could use all of the machinery that we used before with artificial censoring, but here, as you might imagine, you're going to get a lot less artificial censoring as you make M bigger, because basically this is saying you're allowed to do whatever you want in the grace period. You just have to start once you meet the criteria by the end of it. So you can imagine if you made, as M goes to infinity, what that's saying is I'm not going to intervene on you at all. So you get a lot less artificial censoring. Whether this is your question or not, right, this is where we have to decide. So we're better supported for this question, but is it really the question we wanted to ask? There are actually two interpretations of these grace period interventions. One is during the grace period, just simply don't intervene, assign treatment according to how it's assigned in the data, and because I didn't intervene in HIV causal, I have no idea, it could even depend on you in those periods, who knows. But another way to interpret these grace period interventions is to say during the grace period, assign treatment initiation according to a random draw from the observed treatment density. So these actually might sound like the same thing, but they're not, because if treatment was not assigned according to this, then when you go to a future population, if you chose to implement this strategy versus this strategy, you might get a different answer. And as you might imagine, the latter one requires stronger assumptions because this one allows treatment to be assigned however, whereas this is restricting it to be assigned based on L and A. And so the latter would be an example of a random dynamic strategy because it's talking about a rule where treatment is assigned according to an intervention. So I have a lot of sort of some technical thoughts on random dynamic strategies. Let's skip that. We have a couple of minutes before the discussion, and you just shout to me when I should stop talking because I probably could talk for more than 5 minutes here. So the parametric T formula. Sorry, what was that? Oh,
I'm to finish up the G formula, especially regarding the difference between the G formula and MSM, please.
Yeah, no, so this kind of will get into, I think, some of the stuff that everybody wanted to discuss anyway. So, so the parametric T formula is another approach that can be used to estimate effects of time-varying treatment strategies. Unlike IPW and unlike TMLE, it requires consistent estimation of the full observed data likelihood. It does provide one sparse data solution in the face of near positivity violations, and I put solution in quotes because it does so by imposing a lot of model assumptions. And on the whole, you could easily argue that these assumptions are much stronger than those imposed by any MSM, although that really could depend on the scenario. Another problem with the parametric G formula is this phenomenon called the G-null paradox, which basically it's been shown, or you can prove that under no causal treatment effect, in a scenario where there's no effect of treatment at any time, but you have time-varying confounders affected by past treatment, you can actually show that some model misspecification can be guaranteed under estimating this full data likelihood using standard parametric models. There are some special cases, and in practice, it's not really clear. This is sort of a very large sample issue, and we've certainly used the parametric G formula and failed to reject the null many, many times. So we're actually planning to do some simulation studies to look at how this plays out in various scenarios, but this is a problem, particularly if you're planning to do null hypothesis testing. So given all of these problems, why would we use this? And one of the reasons is historical. So up until a few years ago, we actually didn't know how to construct semi-parametric estimators at all, IPW or TMLE, for certain types of dynamic strategies. And so, so these strategies were called interventions that depend on the natural value of treatment. So there's reasons, I don't have time to get into it here, but you can look at some of these papers, this one and this one, if you're interested, on why we might want to consider these interventions. And one of them is that they give us a way to, they give us a way to define the effect of maintaining a continuously measured treatment within some specified range. So at that time, up until 2014, up until this paper, we had no idea even how to derive an IPW estimator for these types of interventions. So at that time, the parametric G formula was the only way to estimate some of these questions, and that was really when we started building software for it and using it a lot. And there's actually currently still no, so we describe an IPW estimator in this paper, there's still no way to estimate these particular interventions using TMLE. I mean, I'm sure that you can derive it, but nobody has, and there's currently no software. So as of today, there are certain questions for which the parametric G formula is kind of the only way to use it, or we have an outline for an IPW estimator, but that hasn't been applied to my knowledge. Another reason why we use it is that in general, implementing two methods that rely on constraints on different components of the observed data distribution can be confirmatory of our conclusions. So in practice, now again, this is not true across the board, but in my experience, and actually I just came across an archive paper, which I was hesitant to post here because it's an archive paper, it's not peer reviewed, but I think the first author is Schoenfeld, and he does a really, from Cape Town, and he does a really nice comparison. I don't even know him. I don't know him, and he has no affiliation with me or with Berkeley or anyone that works on these methods, I think, but has a nice simulation and applied comparison of the parametric G formula, longitudinal TMLE, and illustrated that when, and I've seen some of this in my own work in comparing the parametric G formula and IPW, that when you have a lot of data that well supports the question, in other words, you don't have a ton of artificially censored subjects, you don't have near positivity violations, you're going to tend, in my experience, to get similar, not drastically different results with these different methods. They tend to be the most drastically different when you have sparse data problems, like near positivity violations and other issues. And that's when, in the case where all of these methods really break down. So while TMLE has really good theoretical properties, and probably you should always use it, include it as one of your methods when you can, if you have really good data to answer the question, you're probably not going to get a drastically different answer in practice if you use TMLE versus IPW. Maybe you might with the parametric G formula. I'm not going to say anything definitively here, but that's been my experience. It's when you don't, then you're going to find all of these methods, well, TMLE and IPW are going to severely break down because these are more data-driven methods. So you can implement them in different ways under, as we just showed with IPW, and the same holds for TMLE under, say, marginal structural models or other assumptions, pooled over time models for the weights, for example, that make more assumptions. Those methods are going to tend to be more honest with you when you just don't have the data to answer the question. Whereas the parametric G formula is going to tend to be pretty stable unless you are really, really flexible with your modeling. And so then you have to decide, so if you see very different answers, using more than one method can actually be informative in that it gives you a sense of whether really I shouldn't be asking this question and I should probably tweak. So that's one reason why you might want to use IPW, parametric G formula, and TMLE, or some combination of them. And as I said before, there are certain questions for which TMLE is not currently available. Also, I just note here this TMLE is developing at a really rapid rate. It's really becoming a very practical, much more practical method. For example, I don't know this, I'm not 100% certain about this, but I'm pretty sure, for example, the LTMLE package that Maya talked about in workshop 2 does not allow, for example, pooled over time models. I apologize if I'm wrong about that, but whereas this very new package, the STREM-R package, which just came out a couple of years ago, does allow pooling over time, and I think they call this the long format TMLE, which is much more feasible when you have many, many time points. So you can imagine that when you have 60 time points, as you get further and further out into the follow-up, you're just going to have fewer and fewer records. So you can't pull over time. You're just like, and then you try to throw super learner and sort of aggressive machine learning algorithms, it's going to just not work. So there are developing more and more implementations of TMLE that work. My understanding is well with real world high dimensional data with, sort of these very long follow-ups. I think that was the purpose of STREM-R. This is kind of my thoughts on the comparison. Another potential advantage of parametric G-formula, which again, I think is really very specific to the scenario, but something I noted several years ago, that while it's a disadvantage that, so I actually didn't go into the algorithm, but one of the features of the parametric G-formula is that you have, again, because you have to estimate the whole data likelihood, you have to estimate the joint distribution of the L's, the time-varying confounders. And that's one of the reasons that, this is so highly subject to model misspecification. But the flip side of that is that it allows you, if you know something about the distribution of some of those L's, it allows you to incorporate it. So I talk about an example of this in this 2011 paper, and also, as I say at the end, I have a slide at the end, we actually did a CIMPOD workshop on the parametric, that was fully devoted to the parametric G-formula in 2017, and I have a link to the end which has slides. We have a SAS macro to implement this with sample code and examples of the code. So I'm not going to spend a lot of time on the algorithm here because you can go and have much more detail in that workshop. But I talk about some examples there of how, particularly in HIV causal, we were able to incorporate a priori knowledge. And then the last thing is, again, just a practical thing. And of course, you always want to get the best answer possible. You don't just want to do something because it's computationally easy. But one of the advantages from an algorithmic point of view is that the parametric G-formula algorithm changes very little once you start changing the strategies. So basically, so I'll take 1 second and just go through the algorithm. So this basically estimates the G-formula so that, again, that expression, that high dimensional sum over the L bars, by estimating each component with parametric models irrespective of the strategy, and then conducting a simulation, basically, where you generate the confounders and then assign the treatment according to the rule G. So the only step that changes by changing G is just this, how you assign treatment. So you can, whereas as you saw with the IPW approach, and this translates to TMLE, which also requires weighting, you have to do the whole process of artificial censoring. It becomes, the whole algorithm has to be redone for each question that you consider. Whereas with the parametric G-formula, you can sort of consider all kinds of strategies with very little tweak to the algorithm. But you could also argue, understandably, that's dangerous because you're sort of, oh, I can answer anything, but you're totally relying on this estimate of the joint distribution of the data. So that's why I tend to limit my use of the parametric G-formula to questions that can only be answered, at least for now, with that algorithm. For example, natural treatment value interventions, or as a secondary method, as a way of sort of evaluating how bad near positivity violations are, how well the question is supported by the data. I think that's it. So as far as the parametric G-formula goes, if you're interested in checking it out, we do have a SAS macro that we spent many years developing for SAS users, but we are also now developing an R package. It's very close to done, and I was hoping it would actually be up there now, but it's taking, as everything often does, longer than expected. We have the CIMPOD 2017 workshop materials, and I think there was a YouTube video of the workshop, which the sound is very bad in the first few minutes, but then it gets better. So that's it, and some references, and this is just the start of that stuff about graphical evaluation of exchangeability for anyone who's interested. So should we do questions or?
Yes, thank you, Jessica. That is excellent. I have several questions coming in from chat, both chat and the Q&A function. Let me go through those questions. I'll just read the question to you, and I have already, sent a message to the attendees, letting them know that we potentially can extend the workshop sessions to 1:15 if necessary. Okay, so the first question. Are there certain type of treatment strategies that are better answered by IPW versus G formula?
Well, so again, I think the idea is that when the data is when the question is well supported by the data, then either approach is probably, if you implement them with flexible enough models, either approach is going to hopefully give you a similar answer. They just make different assumptions. So I would argue that if you can get away with using IPW, which makes fewer assumptions, and the weights are fairly well behaved, and it's a question that you can answer with IPW. Like again, so for example, here's an example. So if you tried to answer a question, there's a lot of feedback. I don't know if everyone else is hearing that, but I'll just talk over it. So if you had a question like, I want an intervention where I set treatment dose at every time to 10 milligrams over a long period of time. And treatment dose is highly varied in the population. So really dose can be viewed as a continuous variable. It's going to be, the chance of anybody having exactly 10 milligrams is going to be, there's going to be very few people that are continuously following 10 milligrams. So that's an example of a question. It's a static intervention, and it's almost worse than what we consider here, because if you tried to do this artificial censoring approach, probably the whole data set would be artificially censored, like you'd have 2 people left in the data. So clearly you cannot use IPW, at least the basic implementation in that case, because it would just blow up. You'd have nobody. Everyone would get a weight of 0, or nearly everyone. So in that case, you have to make some kind of additional assumptions to get around. If you insisted on answering that question, so one option is you could say, once I realize I've artificially censored away everybody, maybe you rethink your question. But what if your investigator you're working with, like I've had this experience where I work with medical doctors and I convince them to come up with a question, and then it turns out it's a question that's completely not well supported by any data set, but they just insist that they want this question. Then the parametric G formula is going to answer it. It's just going to make a lot of assumptions to answer it, because it doesn't require that anybody it actually doesn't require that anybody even have 10 milligrams in the data, because you're just fitting models for the hazards conditional, smooth models for the hazards conditional on say treatment dose, and you can smooth. If you make a linear assumption, then it doesn't matter. You're just smoothing away the fact that nobody has that level required under the strategy, and then you're just going to use simulation to assign. So if you insist on doing that, then the parametric G formula is one way to do it. You might be able to get away with IPW with a marginal structural model in that case, but probably not, because the weights are probably going to be, just explode. And so would TMLE, which also relies on weight. So there would be an example where the parametric G formula might be the only approach that gives you a stable answer, but the other methods, doing them in conjunction, would make clear that you have to be very cautious about that answer, because it's probably very susceptible to model misspecification bias. I would just we have a lot of questions, so I don't know that I want to take up 100 years, but you could also, I view all of this as like a spectrum. So, for example, we recently had a symposium with Miguel Hernan's group and the HSPH, and the topic was agent-based modeling. So you could think of the parametric G formula as a little more of a honest, not honest, but a little more of a data-driven version of agent-based modeling. Agent-based modeling is when you have no data and you simply try to simulate what would happen under interventions by either sort of making up distributions and parameters for simulation, or maybe grabbing different parameters published in different papers that don't really correspond to a single population or single distribution. So the parametric G formula is very similar to that, but it bases the simulation on an estimate of the joint distribution of the covariates in at least a well-defined population. So I would sort of think of the case where the parametric G formula would work better is when you really have just very little data to answer the question, but you have some, and IPW would be better, or certainly TMLE, if you have the reasonable data to support the question. And again, some would argue, and I imagine Maya might argue this, and I'm on the fence about it. I mean, from a personal point of view, I would argue it, but from working with real investigators, I would rather them use the parametric G formula and do something sort of principled than just run a linear regression model that has no clear questions specified or no understanding of what we really mean by confounding and, you know, all of those things. So, but I think if you can, it's better to use TMLE or possibly IPW. And then actually there's another approach which we didn't talk about, which could also potentially be used in place of the parametric G formula for poorly supported questions. That's this sequential means estimator. That's kind of, I don't know how deep Maya went into the TMLE algorithm, but there's a step where you sort of include this clever covariate, which is the weight. So basically it's the same algorithm, but excluding that clever covariate that requires you to estimate the, you know, inverse probability weight. So either the parametric or that sequential means estimator might, quote, work. In other words, it won't completely break down in the case where you have something like always treat with 10 milligrams or always exercise exactly 30 minutes a day, or sort of some intervention on a deterministic intervention, let's say, on a continuous treatment would be an extreme case. So I don't know if that helps.
That definitely helps a lot. So next question. This is related to slide number 47.
Okay. Yep.
47.
Is this 47?
Yes,
yep.
47. Okay. So the question is, if you censor him artificially, shouldn't the outcome be missing?
The outcome is missing because, remember, this corresponds to the status at time k. So basically what I have, you can think of this data set as representing the counterfactual world. Of course, it doesn't, because we have to make a lot of assumptions for it to assume that, but you can loosely think about, for individuals who are following the strategy up to a certain point. So basically this record up to here, so through the 3rd month, this person's data, including their outcome status, is consistent with their counterfactual outcome status under the regimen 350 because they're following that regimen. But here, after this point, right? Oh, I see. Oh, I see what you're saying. I actually said this. Yes, this should be coded as NA. I see what you're saying. On that line, it should be coded as NA. Is that what, I think that's what their question is. Yes, that was a mistake on my part. I'm sorry.
So it's a typo. So at the 4th line, at month 4, we should replace 0 with a dot.
You know what? I'm going to put a caveat to that. It's actually okay to keep this as 0. This becomes kind of one of those interval ordering assumptions. So remember I said that I assume that No, actually, you're totally right. Yeah, no, this has to be NA. I can actually correct that and repost these slides if that helps.
That's no problem, Jessica. Don't worry about it. Thank you for your clarification.
Yeah.
So, next question. Can you further clarify why we need to impose artificial censoring for dynamic treatment strategies and not static treatment strategies?
Well, so you can impose artificial censoring for static treatment strategies. Like, you could follow this exact procedure for static treatment strategies. It's just, as you can imagine, it's a pain. So what you can, because you have to go through the whole process of making copies, enumerating every strategy that you want to consider. So actually, I guess I didn't clarify this well. You can really think of, where was that part on static? Yeah. So really what you can think of this approach where you don't artificially censor in the case of static strategies, you can think of just we could have not artificially censored and made copies in the dynamic strategies, and just sort of, so here you can see, for example, in the dynamic strategies case, this individual one is actually following both strategies up to a certain point, right? So he's artificially censored, he's following 350 to here, and he's also following 450 all the way through. So for these first 3 months, he's contributing to the hazard estimate under both 450 and 350. But I wouldn't have been biased if I just simply ran for anyone who's following more than one strategy, if I just randomly selected one of their strategies to consider, to include towards the estimate of risk under G1 or the hazard under G1 versus G2, that would not be a problem. It just would be less precise. So we can think about that's what I'm doing here. I'm just grabbing the strategy that they were following through each time. So let's see. Actually, in this case, so let's think about an individual who started treatment right at time 5. So that individual through time 4 is following the strategy start at time 5, 6, 7, 8, 9, 10, and so on. And they're also never initiate up to time 4. And so they're just going to be, their data is going to contribute. Everyone who has zeros through time 4 in the actual data is going to contribute to that strategy based on this function of A bar K. So I'm not sure I'm explaining this well, but does that help clarify? I'm not sure who asked that question. Yeah.
So Jessica, next question is related to the last question.
Yeah.
Static treatment strategies. Do we also need to make copies for each G in the final weighted dose response model?
No, you don't. So again, the idea is that because everybody, in the case of dynamic strategies, there are going to be some individuals who aren't following any of those strategies. So you have to be explicit about, you can't use a bar itself as a determinant of whether you're following the strategy. You have to use the whole history, which is why we have to go through this explicit artificial censoring procedure. But here, I should have actually maybe created some data set examples, but here the point is that you're going to be contributing by just using this algorithm without artificial censoring. It's like all people, right? Here's a better explanation. All people who happen to have, let's say we consider through k equals 0, through k equals 3. All people who have the pattern a bar 3 of all zeros are going to be contributing to an implicit copy, to a copy that is a strategy that involves no treatment through time 3. So the fact that we don't make a separate copy for each individual for every possible static strategy where you could have no treatment through time 3 is just an issue of precision. But we could do it. We could enumerate. So basically, we could enumerate every single one of these strategies, just the way we did for the dynamic strategies, make copies for all of them, and censor people as soon as they, stop following the strategy for that copy. That approach would be sort of asymptotically, or as n gets larger and larger, would converge to the same thing as this. It just would be, this would be more variable, because each individual is only contributing one of those strategies. It is only, let's see, each individual is going to contribute themselves once to each of those strategies. So it's just an issue of precision. So again, we could, if we had the same thing with the dynamic strategies where we found that, say, we considered 4 strategies and one individual contributed data to, was not artificially censored through time 3 in all strategies, that is a more efficient procedure than simply selecting one of his copies, contributing his data towards one of those copies and just selecting it randomly. That's what this is effectively doing. But we could, and it would be correct, to do this approach with just the same artificial censoring and copying approach, but it's just easier to do it this way, even though it's a little less efficient.
Okay, next question. For continuous outcome Y, can Y underscore K be used as a part of time-varying confounder? For example, clinicians may want to change medication from one to the other after looking at the patient's outcome.
So, right, correct. So you have to define one outcome. So for example, if you said like, so for example, we might have considered a scenario where CD4 cell count at 5 years is the outcome, right? So a non-survival outcome. So in that case, prior CD4 cell count would be part of the L bar K. It would be a time-varying confounder, but it's actually not the outcome. You have to define one outcome. So in this case, the fact that we have sort of time-varying indicators is because we can think of the outcome as being like a failure time T, and this whole history of indicators makes up that outcome, if that makes sense. So yes, it's correct that you would include, in the case where you have a non-survival outcome, I'm trying to find where I wrote the exchangeability assumption.
Yeah. So we need to differentiate.
Anyway, so like if CD4 cell count was Y at 5 years, then half CD4 cell count would definitely be part of the L.
Great. Next question. How can we handle the data with different time interval? For example, in claims data, drug, treatment, and covariates are not measured at a fixed time interval. Can this method still be applied to that case?
Yeah, so that's exactly the scenario of HIV causal, right? That's like a clinical cohort. So people are not coming in at fixed times. They're coming in whenever they have a visit, and that's when you're measuring things. So yes, it can be used. So the way we handle that is, first of all, the L's are going to include a visit indicator. So when I said a lab measurement here, you can also think of that as a visit indicator, right? So so in our case, it was a little bit mixed, because if you think of Y as like mortality status, you could get that from death records, right? So that's not tied to when a subject comes in. And A was available in prescription records. So we pretty much had access to this. But the L's were very much contingent on people coming in for a visit, which is why we censored individuals when they did not come for 12 months, because we felt that we could not trust that treatment changes were not due to changes in L's that might have been assessed elsewhere that we didn't have in the data. So in the extreme case where everything is being assessed only when people come in for a visit, you have to make decisions. So for example, you might have a much stricter censoring rule where you say, I'm going to consider part of my intervention that everyone is observed, you know, every M months, and you're considering interventions every M months, right? And so then you have to make stronger assumptions on censoring. So there's a nice paper by the first author is Miguel Hernan. It's called, the title is Observation Plans in it. And it talks about these types of decisions that you have to consider with respect to the measurement process. But yes, this is a ubiquitous problem. Most studies have a variable visit process, and the visit process itself can be a time-varying confounder and also might be needed as part of your censoring definition if you sort of feel, in order to answer the question, you have to insist on more frequent visits. So you're basically, what you're targeting is the effect of different strategies under an intervention where people are frequently monitored at some frequency.
Okay, we have time for one more question. How to evaluate whether weights work?
Sorry, how to evaluate what?
Whether the treatment, the estimated weights work.
Oh, whether the weights are, you know, adequate or whether they're not extreme?
Yes.
So you can look at the distribution of the weights. So if you find that the distribution is highly skewed, then that's a sign that either you might want to consider a further approach to stabilization, maybe at the expense of more assumptions. You can take the approach of truncating the weights, which is again going to be kind of a bias variance trade-off. So by truncating the weights, you might say you know, I'm going to truncate weights that are greater than 10, or I'm going to truncate them at the 90th percentile of the distribution of the weights. But I think another nice way to assess whether, you know, extreme weights are causing, or basically near positivity violations are causing a large problem in your IPW estimator, is to look at another method again. So that's something that's often, it's not formal, it's sort of ad hoc, but that's what a lot of people recommend, is to look at, say, a non-weighted estimator, and do you find, you know, you're getting similar results, or if you can also look at, you know, sort of, right, is the weight distribution skewed? Is the mean close to 1? Is the mean very different from the median? But again, some of these decisions are, everybody struggles with these decisions because there's so many different ways to do this, and this is why often looking at more than one method can help assess, you know, whether you really need to tweak your question. Because I didn't get into sort of random dynamic strategies, right? I talked about one example, but for example, the big problem with deterministic strategies is that fundamentally the numerator of the weight is 1. And so you can do these stabilization procedures to put something that's between 0 and 1 in the numerator that hopefully brings the numerator closer to the denominator. But if you consider random dynamic strategies, where you basically define the intervention as assigned treatment according to some distribution, well, the real treatment is assigned according to a distribution. It's the observed distribution of treatment. So you could actually, if you know, to really guarantee that your weights are well behaved, you could define the intervention, for example, and there are some recent papers on this, and we've written about this. I have some slides on this that I didn't cover, so you can take a look at those. I'm trying to go to it now. Where you define the intervention as like just a small shift in the distribution of observed treatment. So there's a paper by Munoz, Diaz, and Vanderlaan that describes that, and we've described other ones. Where is this slide? So anyway, that's one way to sort of, really what it all boils down to is to truly define a question in a way that's close to the data and well supported by the data. Basically, you're saying, I'm going to consider an intervention where basically treatment is assigned as it was in the data, but with just some small shift. Now, that might not be the question. That's a hard question to explain to a scientific, to a medical doctor collaborator. And so you might not be able to get away with asking that. And then, so in the case where you do have to deal with extreme weights, then you want to look at the distribution again. You can consider other methods and see, do you find generally the same answer that's comforting, because it would be unlikely that, just by complete coincidence, all of the problems in both methods would cancel out to give you the same answer. And in the case where you see highly different answers, you might have to, either just report both and then you have a range, or you try to convince your collaborator to sort of tweak further.
Wonderful. It's 12:15. It's time for us to end the workshop. If you have further questions, feel free to send me the questions. I can forward it to Jessica. And we will make the recordings and the slides available to everyone later this week. I want to thank you for joining the workshop. Thank you, Jessica, for your wonderful presentation. Goodbye.
Oh, it's my pleasure. Thanks. Bye.